Okay, so what will most likely happen today is going to be our second last meeting. We'll have one very short one. There's of course still a lot more to discuss, but I want us to kind of move on from this a little bit. And then we'll start working as an actual reading group instead of just me lecturing. Probably either studying, we'll have like 2 meetings next week, like one short one, mechanics one, and one actual one for the next thing, or maybe next week. So I'll post a schedule for people to sign up, which days they want to present. So we'll probably have like 1 or 2 people present each week on like a chapter or something. And that will probably be live streamed on Zoom. I will keep a recording like private, but I won't like actually publicly post it for that. Yes, we'll start. The next thing we're going to do are going to be ODs. Yeah, so we'll just do ODs following Arnold's book. I got one for a while. If people want a physical copy, if you don't want a physical copy, well, I'm sure there's books online. Okay. So let's briefly review what we talked about earlier. So if you may recall, we wrote down our previously postulates of quantum mechanics, right? So we had a few postulates. First one was space was a public space, and the state of the system is fully described by some vector in the filter space. 2, I'm not explaining everything in full because hopefully this is just review. 2, any physical measurements is associated with an observable. So with self-adjoint, to open a door, you twist the handle and you push the door forward. Associated with self-adjoint linear operator. So I'll just call this little space H, operator on this space H. So then we can get that subparts that the eigenvalues are, so let's call this observable, A. The eigenvalues of A tell us the possible measurement, so the possible outcomes of the physical measurement. Outcomes of physical measurement. And we have the following part that if so if the system is in state psi, then the probability then the probability to measure lambda the you take psi and so let me think about this. Which entry do I want things in? Yes, I want things in the first entry. Psi ei squared over, and so the sum is taken over the I has eigenvalue lambda. Yes, so we take dot products of all the eigenvectors of A that have eigenvalue lambda. We take the absolute value square that. This has an extra vector for some reason. And this will give us the probability to measure lambda. Okay? If we are already if we know we're in state psi. And then we have the third point. And so an important remark about this is, so suppose this is a self-adjoint operator. Suppose we have some Hilbert space where we have a spectral theorem. So we can always write down a basis of eigenvectors of A. In that case, what can I do? Well, I can write down psi as a sum of some AI EI, right? So some where EI are eigenvectors of A. Okay. So this is just a statement that A has a basis of eigenvectors. If it's self-adjoint, then that is always true if H is an isomorphic Hilbert space. For example, if it's finite dimensional. We proved it for finite dimensional vector space. Okay. Then this sum really becomes the sum of AI squared for the absolute value of AI squared for EI eigenvector of A with eigenvalue. Okay. So this is so far to remember this. Quickly. The third postulate third part of this postulate that we talked about is that if a measurement is actually made to have eigenvalue lambda, right, then the wave function, the state kind of collapses. Actually, everything that I've talked about is I kind of been implying everyone that the normal of the state is 1. The state is our states are always normalized. Okay, I think that's okay. So if measurement is made on psi, and we got lambda, and then the wave function is going to turn into the sum of psi inner product I, and then you divide by the norm to normalize it. And so this is once again taken. The sum is taken over eigenvector with eigenvalue lambda. So if we measure lambda in real life, we expect that the system will kind of collapse to only include states that have eigenvalue lambda. Right? So that kind of, if we do a measurement again, we're guaranteed to get lambda again, because after we measure lambda once, the state collapses to something that only can give us lambda. Okay? So these are some of the postulates that we've had time to discuss for now, and then we look at like one simple example. In reality, we should really look at like a lot of examples, but we haven't had time yet. Now there's more postulates. But everything that I've told you here happens right into this cat's Let's get that piece. I'm saying my state can evolve in time somehow, and this time of evolution is given by the equation. So where h bar is the what's called reduced Planck constant or whatever it is. Planck constant. And h is the Hamiltonian. So the Hamiltonian is always the observable associated with measuring energy. Okay? So this shouldn't look good. What is unclear from the mathematical perspective in this equation? What is not immediately obvious about this equation from a math perspective? No, the imaginary number is straightforward. We know what an imaginary number is. Okay, why is it there? Well, that's a physics question. Yeah, so this is the differential equation, correct? And that's where we're going to be doing differential equations. You don't need to know how to do that. I'm just saying that if I have a state, then it has to satisfy this equation. That if you take the derivative, you get the Hamiltonian acting on that. Right? The equation itself makes sense, right? You take the derivative of something and you're supposed to get this. And we're saying that any state has to satisfy it. Okay, but which part is not clear from a mathematical and physics perspective? Which thing do we not really want to do? Okay, the Hamiltonian is linear operator. Surely you know how to apply linear operator to a vector in the vector space. Okay? That's fine. There's like one thing left. There's a equation that hasn't been studied. No, that's just a math. That's fine. There's one thing left. Yes, you're taking a derivative of some abstract vector in some abstract Hilbert space. How do you do this? Well, it's a function, sure, but this could be. Well, psi does not need to be a function. It's just symmetric. Right? So psi of t is a vector value function that depends on t. Right? Because it's psi of t can think of it as something that goes time into your Hilbert space. Sure. But okay, the question is, how do we take a derivative of something with elements in the Hilbert space? You take the derivative in the usual sense. H goes to 0. You just look at this limit. Right? T equals h minus psi of t divided by h. Okay, this h is not the same as h bar. Okay, but then the problem is, this really doesn't answer anything. Right? Because now your question will be, well, how do I take this limit? Right? How do you take this limit? I'm not going to talk about this in too great detail. I will just remind you that we have a metric on our Hilbert space, right? We have a metric on our Hilbert space, right? Which was given to us by this. Right? So what we can write down the delta epsilon definition for this thing. I think this would be called, you know, strongly convergent or something like this. Like you have different kinds of convergences on these filtered spaces. You can have strong convergence, which is convergence in terms of the norm. Then you can have like weak convergence, which can only account for the inner product. But I don't want to talk about that because otherwise I should be talking about analysis to you for like an hour. And also I did convergence analysis to you now, so I won't talk about it. But I just want to make a remark that the fact that you're taking a derivative of your vector space, even though when we actually compute things, it's going to be completely obvious because it's going to be taking coordinates, and you'll be like just take the derivative in whatever way makes most sense in how you're computing it. But the point is, taking a limit here, there's many ways in which you could take a limit, and then like there's a lot of detail in this. But for practical purposes, you never really need to worry about it, I guess. But there can be a lot of detail. Okay. Yes, makes sense? So now let's look at so you're right, you don't know how to solve differential equations, but maybe you know how to solve a really simple one. And just try to see how solving a really simple differential equation will help us kind of find solutions to the Schrodinger equation. Okay? So let's see. So I'll rewrite the Schrodinger equation now. Right? Now I'm going to assume a couple of things. I'm going to first assume that so the Hamiltonian is time independent. So how we measure our energy doesn't change with time. So this is it. And okay, and then I guess the Hamiltonian is always, since it's observable, is always self-independent, whatever. And so we can say that it has, say that Hilbert space is nice enough, and it has a basis of eigenvectors. Okay. And I guess let's make it further simpler. Let's assume that this basis is countable, so that I don't need to make much more. Okay. So now, okay, we want to in principle solve this equation, right? Let's first look at a really simple case. Okay? Suppose at time t equals 0, my state psi of 0 is really just an energy eigenstate, the nth energy eigenstate of the Hamiltonian. So when I write En, I will always mean a vector such that H applied to En is going to give me En, the number En times the vector itself. So I'm kind of labeling the vector by its eigenvalue. This makes sense? This means some vector with where the Hamilton where it has an eigenvalue with respect to the Hamiltonian of En. Does this make sense, this notation? No? This is a vector, so I will write this symbol to mean a vector that has eigenvalue En with respect to the Hamiltonian. So if I apply H to So in that case, how does the Schrodinger equation look like at time 0? The Schrodinger equation looks like at time 0 as I bar dt applied to r psi, I guess at 0 now, which is psi of t. And specifically at time equals 0, I can apply the Hamiltonian and I'll just have a number en applied to en, right? So times en. So I forgot to think about how to justify this fully reversing. But since the Hamiltonian doesn't change with time, right? At any point in time, this will still be the eigenstate of the eigenvector of the Hamiltonian, right? So let's see. We can kind of sorry, I'm blanking what's the right way to justify this. Okay, if they don't come up with how to justify this in the next 10 seconds, I'll just not justify it. 0. Okay, I'll just not justify it. We can guess a solution. Guess that the solution psi of t should be equal to some function well, it should be equal to some function let's call it f of t. Some function f of t is multiplied by the original state at time 0. This is what we will guess if at time 0 you have an eigenstate. We'll guess that this is the initial solution. Okay. Then if you were to rewrite this equation, right? So En is time independent, it doesn't depend on time. So then the equation will look like this. What did I do here? I took the derivative of this whole thing and I just applied product rule. Why does product rule apply? It does. You can check that on your own if you read about how this weak convergence or strong convergence stuff works. You can check if you have a product rule for a function multiplied by vector. Since the vector is time independent, right? And then the product rule is arbitrary 0, so you're just left with dt of f times en. This has to equal to en f. Okay? Do you see how that very good? Yes? I said suppose this is equal to this. Like assume that this is equal to this, then I have to get here, I get this. Yes. Good. But now you can see, okay, this is the same vector, this is the same vector. By uniqueness of expansion of stuff in the basis, I know that this coefficient has to be equal to this coefficient. Do you agree? Should start using differential. So in this case, I just get this differential equation. I will rewrite this. I have ddt of f is equal to minus I over a bar times en. Okay? So this is some constant, and this is my function again. Okay. I just Okay. So now, okay, do people know how to solve this? I think you do. No, I just want you to give me the function that solves this. You know, the function. Yes. Yes. So f of t is equal to e to the what? E to the minus I over h bar over en d. Okay. Yeah, sure. But okay. Do people see that if you take the derivative of this function, you get this? Okay, that's it. I don't want to spend more time. So this is kind of, so what do we get? So we get that the following. If initially we are in our, if at time zero, the state is just some energy eigenstate, then a solution of the Schrodinger equation is that at time t, the state is still the same state, just multiplied by a phase that depends on the energy of that eigenstate. Okay? So this is a solution to the Schrodinger equation. If you spend some time, which I should have prepared, you can show that under nice enough conditions, the solutions to the Schrodinger equation should be unique, and so you know that this is the solution. Or at least I think under enough conditions things are unique. From what I remember. I need to okay, just trust me that this is the solution. Okay. So this is at time zero, you are an eigenstate of the Hamiltonian, then all you do is you just like pick up some phase over time. Okay? So now let's just solve the Schrodinger equation generally using this idea. So suppose at some initial time, so now we're going to write this as follows. So suppose at some initial time, I was actually some linear combination of energy eigenstates. Any linear combination I like. Okay? At time zero. Then, question, what is my state at time t? Very easy. And the very easy part should come from you noticing that the Schrodinger equation is linear. Right? The Schrodinger equation is a linear equation, meaning that if instead of psi, I replace psi with psi plus some other phi, then the equation still holds on both sides. Sorry. In this case, we get that if psi and phi separately solve the equation, then psi plus phi has to solve the equation as well. Right? Do people see that in the equation? If psi solves it and some other phi solves it, then psi plus phi has to solve it. Because taking the derivative is a linear operation, and h is also a linear operator by definition. Okay? So if two things are a solution, then there's some, their difference, their scalar, whatever it is. There are any linear combination is also a solution. So if we know that each of the EIs has, this solution, then the sum has to be the final solution over time for the whole thing has to be what? Has to be AI what? Yes. EI T E. Let's go back to using because we have Okay. Great. We now, in principle, know how to solve Schrodinger equation. Now, important part. Notice that these ENs in the exponent, they're of course all different ENs, right? For different eigenstates, if the eigenstate has a different eigenvalue, you have a different EN. Now, one thing that I also kind of swept under the rug is I labeled the energy eigenstates by EN, but you know that you could in principle have a linear operator that has eigenvectors and a bunch of eigenvectors have the same eigenvalue. Right? You could have something that is like, you know, I could always write down a matrix that's like 1, 1, 1, 0 here, 0 here. This is self-adjoint, and okay, there's 3 eigenvectors, all the eigenvalue 1, right? Okay. So if you have something with the different eigenvalues, you need to be careful and like you can't just index things by EN because you have multiple things with the same energy. So you need to add like more indices or something. Okay. That's straightforward. The equation still holds here. If you have eigenvectors with the same different eigenvectors with the same eigenvalue. Okay. Okay. So I think there will be quite a few suggested exercises for next week, which I hope you will do. And I think one of them will involve like maybe plotting some solutions of this and how they evolve over time. Something like that. Okay. We have 10 minutes left, and this is what I thought to spend, you know, a smaller part of the time on. But that's okay. I will skip explaining the matrix exponential maybe because we will see that in ODEs anyway, and I guess I'll just not talk about it now. But okay, let's talk about the expectation value. Or okay. I guess I will erase the for regular equation, like complete basics of it is straightforward. Yes. Now everything I've kind of shown you is for this kind of basis countable, like really nice case, but you could in principle do all of the same stuff where you have wave functions, right? And I think that's what you will have on your suggested exercise. Okay. We'll see that. Okay. Next week maybe we'll do a more next week we'll talk about this maybe slightly more detail. Okay. Now let's talk about the expectation part. So it's funny, everything I told you just now is just like the first page and then it's not the page stuff. When you end, you have to leave, but you can finish watching the point later. Okay, what do I erase? I will erase. Actually, I kind of want that. I will erase this because this is not carrying much information. So now what we want to do is we want to actually think of very vaguely and very loosely about, say an experiment and what we might care when we do an experiment. So suppose I'm in some initial state, right? It is made up of some eigenvectors of the Hamiltonian, right? Suppose let's say I'm measuring energy, whatever it is I measure. If whatever it is I'm measuring, yeah. Once I do a measurement in real life, like a physical measurement, right, my wave function collapses, okay? And it only starts giving me the certain eigenvalue. And it collapses whatever I measure. And whatever I measure, I just have a probability of measuring that. state, recreating the exact same state. But perhaps I don't exactly know what state the particle is in. So I want to do an experiment to try and figure out what the state is, or what the state could be. So I can prepare the particle to be in the same state each time, and then I can do a measurement on it. Right? And I know that okay, with some probability I can measure this thing, with some probability I can measure that thing, with some probability I can measure that thing. Suppose I make a single measurement and I measure lambda. Does this tell you much about what state the particle is in? No. Right? Because there was some probability that I measured this, but maybe it was like 1% probability to measure the thing I measured and I got really lucky, and actually the state is mostly, has most of the probability that the state is distributed to measuring something else. Okay? So ideally what you want to do is you want to take do the same experiment many times on the same state, and then you'll have some you'll be able to figure out what the probabilities are to measure an eigenvalue and try and figure out this. One thing that is really important in this kind of statistical approach is the expectation value. Have people heard of what the expectation value is? Yes, no? That's fine. So we'll define the expectation. So the expectation value is something that you generally see in statistics as well. So suppose I have some outcomes lambda with probability p of lambda. So I have some outcomes lambda, and each one has a probability p of lambda to occur. Yes. That's good. So in that case, the expectation value. So the expectation value of this measurement. So expectation value is given by the sum over all the lambdas, where I do lambda and multiply by the probability. Okay. And this kind of tells me, on average, what am I going to get? Right? This is essentially a weighted average. People see what this kind of solution. On average, what am I going to measure? If half the time I get 1 and the other half of the time I get -1, on average I'm getting 0. Yes. So this is what this is. Do you agree? So this is kind of the mathematical way to phrase it. Now suppose we go back to quantum mechanics. Suppose we are in state psi and are doing measurements, are doing some measurement. So the expectation value, let's write this down. Sorry that I'm raising something. Let's write this down as like a flat E of some process X. So X is the process this measurement. So process of taking outcomes. So suppose we're in state psi and we're doing some measurements that is associated to observable data. Okay. In that case, my claim is that the expectation value of kind of measuring A this is my plane. Theorem, but it's not really exclusive. And this is going to be equal to psi inner product A psi. And now this is the moment. Remember how before our inner products were always linear in the first entry and skew symmetric in the second entry? Now I'm switching conventions. Now everything is going to be linear in the second entry and skew symmetric in the first entry. Do you remember what this means? Okay. So if I pull a constant out of here, it's lambda, and if I pull it out of here, it's lambda bar. So I swap conventions to physics conventions. If we were to write this in the math convention, then the statement would be like this. But this looks more like this. So we will use this convention. And so what physicists is often right, if instead of writing psi, you were writing psi as, like this, then you can see that this is really just like, you can write it kind of like this. And that's why this notation makes sense, because this is kind of like, instead of writing the psi. Okay, this is just the inner product. Okay? So let's do proof. Proof by it's so very obvious. Okay, you can watch this. Okay. So proof. Well, our observable has the basis of eigenvectors, right? So, and I will kind of assume right now, that the basis of all the eigenvalues, there are no repeating eigenvalues, those two vectors have the same eigenvalue. It's important to have identities, but if they have the same eigenvalues, then the same result would hold, the same proof would hold. You just need to be less careful about the instances. Yes? Does that make sense? So assume A has a basis of eigenvectors. I with I value lambda I. Okay, and suppose that all of lambda n equals lambda j in this calculation, or you could equivalently not assume that and still get it. Okay? And so here we're going to use postulates a little bit. So, okay, let's just compute what this is. Okay. So this is the product of psi with a psi. Very good. So now, let's just expand this in terms of the basis. A I T I, and then A applied to this time A I D I. Okay. What is A applied to the I? What is? Yes, it's lambda I E I because we said these are eigenvectors. Very, very easy. Okay. These are eigenvectors of an observable, right? So the eigenvectors of an observable have to be what? If it's not the same eigenvector, then they are we're talking about each other, right? Remember we proved this? So in this case, out of this sum, right, I'm taking the inner product of this thing with this thing. The only term that will survive, I'm taking an inner product of a vector with the same vector. Because all the other terms will be zero because EI is perpendicular to each eigen zero. Yes? So this sum is straight up going to just become a single sum over I of AI times AI bar we see how we went from this step to this step? Yes, good. Okay. What's the inner product of EI or EI? 1, because they are orthonormal eigenvectors. AI times AI bar, that is just the norm squared times lambda I. Now, if you look very carefully at your postulate over there, the sum AI squared with eigenvalue lambda gives us what? The probability of measuring lambda. And so here, if you assume that all the eigenvalues are different, then you see that this is just P of lambda I times lambda I, which is exactly how we define the expectation. Do you agree? If you had eigenvalues that were like the same multiple vectors have the same eigenvalue, then you kind of group things based on eigenvalue, right? Then factor out the eigenvalue and have like a sum of a bunch of AIs over the same eigenvector over different eigenvectors with the same eigenvalue. But okay, that's still kind of will give you the So this sum is always taken distinct lambda I. So lambda I such as the lambda. Okay. Do people see what this is saying? So now what does this tell us? If you are in state psi and you want to compute on average what will my measurement be, all you have to do is take psi, inner product with a psi. Yes, very easy. So we have a computational, like an easy computation that we can do to compute this. Okay. Now, so this is the expectation. Now let's remember another bit of let's keep the question for a little bit. Let's remember another bit of statistics that you all hopefully remember. It is you have this thing called, I don't remember what it's called. Is it like the variance? It's the standard deviation, right? Something like that. Yes, the standard deviation. So the standard deviation tells you kind of how far away from the mean is your sample located. Right? So how much does it deviate? So let's kind of once again do a more mathematical definition. So the standard deviation. So the standard deviation of some I guess some outcomes outcomes of process X. So I guess sigma sub X sigma squared is given to us by the expectation value of kind of doing this process, measuring the process, subtract the expectation value of the process itself, all squared. Okay. So let's write this explicitly. So here we would be summing over all the possible outcomes, and then we'd be doing the possible outcome minus the outcome that you get on average squared times the probability of getting this out. Okay. So I'm just I'm taking my average outcome, right? Looking at some outcome that I could possibly get. this is the average over the average outcome you get. This is what we just did in the previous page. It's given. So yeah, this is an x. This is an x. This is like it means this means this. Just assume that this means kind of a, this is like the if I make a measurement x, make a measurement x minus this minus the average measurement. So I can measure lambda, the probability of t lambda. So I compute the measurement minus what I get on average, square that. So this is kind of the distance to what I get on average, square that, multiply that by the probability. And I sum over this. And so this kind of tells me on average how far away am I from the average measurement. Do you see this is? So how far I am away from average on average? On average, how far away am I from the average? Do you agree? Do you see how this intuitively tells me that? Okay. Very good. So now, how do we compute this in our quantum mechanical case? So once again we go back to quantum mechanics, we say, suppose I'm in state psi, and have observable A, right? How do we compute this standard deviation? Well, now instead of calling this the standard deviation, I'm going to call this the uncertainty of A. So now call sigma sub A the uncertainty. In measuring the thing associated with A. Okay. I guess uncertainty is maybe not the best word, maybe the better word is indeterminacy, or something like that, because the more accurate translation from German captures maybe a bit more the spirit of what this is trying to do, but okay, this is fine. Alright, so how do we compute this? Well, you can notice that this is really, the computation for this should be the same as before. So this is the expectation value of something like this. So I can just replace this, so kind of by previous part, so by previous slide, by previous board, which you cannot see, we have that, so the uncertainty of A has to be given by, so the uncertainty of A, and this really should be in state psi, right? Because the standard probability distribution of what are my probabilities of what I can measure are determined by what the state is. Right? You sure? So, but you know, writing like a sub-index A sub-index psi is too much, so we don't like this for now. But you know, assume that we're always in the same. So this will just be quite in a straightforward way. Okay. Where this is really, this isn't just a number, let's be more clear. So this is a number, right? Remember? The expectation value is a number. Yes? And this is and this is just the identity. Well, the identity of So now, what you would do is, okay, to check that this gives me exactly this equation should be fairly straightforward. It's the exact same computation you did before. Extend everything in a basis of eigenvectors, right? If I apply this operator to an eigenvector of A, okay, then any the identity just gives me back the eigenvector multiplied by this number. A is going to multiply it by lambda. Okay, I do it twice, so I get the thing squared. And then once I do the inner product, I pick up the probability of that.
So the eigenvector. Why do I know eigenvector?
Because this has to be an operator that acts on the vector. Right? If I just throw down a number, that's just it's not clear what I mean, so I'm going to write the identity. But then writing the identity here takes too much time. So I will not be writing an identity, but usually when you see like some equation in terms of linear operators, and then for some reason there's just something that's just a number, even though it should be a linear operator, that usually implies that's the identity multiplied by that number. Okay? Good. So now, yes. Now let's do a simple computation. Okay? So this is multiplication by a number. This always commutes with A. So the identity times any operator A is equal to A times any is equal to A times A. So sorry. I is composed with A is equal to A composed with I. Okay, this is obvious, yes. And okay, same thing for multiplying by numbers. You can multiply the vector by a number first and then apply A, or you can apply A and then multiply by number, because these are all linear operators, right? The definition of linear maps computes with multiplication. So let's compute something. Let's expand this. So if I expand this, I'll get A. So all I do is I'm just expanding this with brackets. I get A squared, right? So apply the operator A twice. Then I get minus A composed with minus identity composed with A minus, so minus A squared composed times identity, and all of this is applied to my state side. Do you agree? I just expanded this. Do you see how I just expanded this? So now I can use linearity. I can write the following. Oh, sorry, this is, I forgot, this is 6 squared. I'm sorry. So now I can just use linearity now of the thing. Sine A squared. Okay. Minus. I can factor out the number here. Sine A plus. So in the last step, I just use the fact that side inner product size is 1. It's different. Otherwise, you see what I do.
Should be outside.
Oh. Yes. But now, what is this? And what is this? This is exactly the expectation value of the measurement associated with A. So this is in fact the same thing as this. This number is equal to this number. Do you? So then let me rewrite this again. And what is this? This is the expectation value of what? A squared. So this is the expectation value of A squared in the state time. This is minus 2 A psi squared plus A psi squared. So I can expand this as the expectation value of A squared minus the expectation value of A squared. Okay. See, so this is kind of a bit confusing. Here is the expectation of A squared, and here's the expectation of A all squared. So this is not the same number. Okay? So now we have this kind of really nice way of computing this. Or alternatively, you could write this as the expectation value of A squared minus A psi times the identity of this. Oops, this is also okay. Do you agree? Okay. So this is our answer. This is how a simple formula to compute uncertainty. You can just if you know what station, you can compute this number, you can compute this number, you can subtract. Good. Now it sucks that this board isn't full. Now I'll go over to the blackboard, erase that board, and I'll write on this board, and then we'll finish. Hopefully we can do this in the next 10 minutes. Will you please go ahead? And we'll raise postulates. So now we will derive the Heisenberg uncertainty principle. Or at least prove it. And then you'll have a question on this suggested exercises, also kind of related to the uncertainty principle. Right, I need to then, if I'm giving suggested exercises, I need to start hosting office hours. Okay, I'll send like 1 billion letters in Excel for setting up all these things for the summer. Okay. So now we will state the Heisenberg uncertainty. First, we need to recall a few things. Remember, we were talking in our specific example with the particle in a box, right? That we had this momentum operator, which was I h bar minus I h bar partial x. Okay, and then we have this x operation, which is just multiplying function by x. Right? And one thing we computed, or maybe we didn't, but okay, it's easy to compute, that the commutator, meaning x composed with p minus p composed with x, is really just I h bar times the identity. Okay, this is times the identity, but okay, people usually just write this as I h bar and not include the identity because it's easier to write it that way. Okay, do you agree with this? means this. So the commutator between two operators is AB minus BA.
What does it tell me?
It tells you the difference between this and that. This is how it's defined. So the commutator tells you kind of to what extent do these two things not commute. Okay. So this is saying that if I was to commute these two things, I'll be off by some factor of I bar. That's the next explanation. I mean, this whole commutator stuff is kind of a big part of quantum mechanics because a lot of the things that happen in quantum mechanics happen precisely due to the fact that things don't commute. In classical mechanics, I can measure energy first and then something else, and I'll always get the same answer if I did the operations in another order. In quantum mechanics, if I make one measurement first and then another measurement, I might not always get the same answer as if I were to do the measurements in the opposite order. Okay? So we remember this? So now this is kind of the theorem, which is called the uncertainty principle. Actually, sorry. Before I state the theorem, I will also remind us of a few other facts. Two other facts. So one was the Cauchy-Schwarz-Minkowski inequality. Which is what? The inequality set that psi inner product of phi, absolute value all squared, has to be less than or equal to the absolute value of thing squared, absolute value of psi squared, times the absolute value of phi squared. Okay? Yes. And you can also take the square root of the whole thing. And this would be equivalent with the absolute value psi phi less than or equal to the norm of psi times the norm of phi. Okay. This is the Cauchy-Schwarz inequality. I think you proved this on one of the suggested exercises. Or no, I think you proved it on one of the suggested exercises. Okay. This is something that you should remember. This is a very important inequality. You should have it memorized better. It's like the most important inequality ever. And then, okay, the other thing that we'll remember is what was it? So, the absolute value squared of a complex number z is equal to, so absolute value of a plus bi squared is equal to the absolute value of a squared plus the absolute value of b squared, which can alternatively be written as the real part of z all squared plus the imaginary part of z, absolute value all squared. Okay. These are the kind of three facts we will use right now. Okay? To prove the uncertainty principle. What's the uncertainty principle? The uncertainty principle says that the uncertainty in measuring x multiplied by the uncertainty in measuring p always has to be greater than equal to some constant which is h bar over 2. We will actually prove like this inequality squared, but that's the same. Okay? X is I take is the multiplication by x. Right? So this was all on some these are operators defined on some space of functions, right? And this would take a function psi of x and give me the new function x times So the multiplication operator by x. Okay. Now we do proof. Okay. So what was the uncertainty? So I'm actually going to square everything right now. Okay. So I'm going to write sigma x squared times sigma p squared. From the previous kind of board, okay, the previous board is mildly visible. So we showed that the expectation value of a squared is actually the expectation of a squared minus the expectation value of a all squared. And you take the expectation value of that, right? So I can just rewrite this. So I have x squared, right, minus expectation value of x psi. So I take this expectation value. I'm not writing the identity because that takes too much time. Okay. And then I do oh wait, sorry. This is not. Sorry, this is not what I wanted to do. This is not what I wanted to start with the definition, not the end part. I wanted to start with the top part. So I wanted to start with the top part. So I will write the expectation value of x as psi a minus expectation value of a squared psi. Okay, sorry. And instead of a, I want to write x. And then I'm going to multiply this by same thing, but expectation value of p. So I just rewrote what this is equal to. Okay. Now, x and p are observables. And in our previous discussions, we showed that on the Hilbert space we're considering x and p are actually self-adjoint. Do you agree? And this is just multiplying by number, and multiplying by a constant number is also self-adjoint. Actually, this is multiplying by a constant real number. Sorry, multiplying by a constant real number. Multiplying by a constant real number is self-adjoint. Multiplying by a complex number is not necessarily. It's not self-adjoint. Okay. So, what is this thing squared? This thing squared is I apply this operator once, and then I apply it again, right? So this is just, when I write squared, I just mean apply the same thing twice. Do you agree? But, okay, this is self-adjoint, this is self-adjoint. So there's difference is self-adjoint. So this, one term of these is self-adjoint. So then, because it's self-adjoint, by definition of being self-adjoint, I can move this to this other side. Just one of the terms. Apply this side. Okay. Yes. What does this look like? What does this term look like? Yes, this is the norm square of a vector. What vector? X minus its expectation value applied to psi, norm squared, times Now what can I do? What can we do? We have three things we can do. You want to apply? Yes, first first. Okay. This is the norm of something squared. This is the norm of a vector squared. So this has to be less than the inner product between those two vectors, absolute value squared. Okay. It has to be greater than equal to absolute value, the inner product of x minus expectation value of x. Applied to psi. Inner product with p minus expectation value of p. Inner product psi applied to psi. And take absolute value squared. Do you agree? Now we're taking the absolute value of some complex number squared. Do you agree? Okay, I'm going to go back to this board now. Okay, we're almost done. I promise. Okay. Okay. So now you can think of this. This is some complex number inside, and we're trying to, do something with this. Right? From this fact, I know that this is just the real part of z all squared plus the imaginary part of z all squared. Do you agree? So obviously, this has to be greater than equal to just the imaginary part of z. Of z all squared. Do you agree? Okay. So what's the imaginary part of a complex number? The imaginary part of a complex number, you can realize that the imaginary part of a complex number has to be z minus z bar divided by 2i. Right? Why? Because, okay, z is a plus bi. Z bar is a minus bi. So that cancels out the a's, and I'm left with 2bi. And so I divide out by 2i. Okay? People believe this? But here, what do I have? Here I have inner product of this. So here I have an inner product of one vector psi with a vector phi, right? But what's the complex conjugate of this? The complex conjugate of this is just the inner product of phi with psi. We remember that doing a conjugate is just swapping. So we get that this previous line has to be greater than equal to. I want to write this. So I want to write this over 2i, where I write this thing like this minus this thing with this. Right? I want to do z minus z conjugate. Okay. So this is the inner product of x minus x, okay, all applied to psi, p minus p, all applied to psi, and then minus, okay, the exact same thing, but in reverse, like the order I have p's on the other side. Absolute value squared. Okay. Do we see how we got here? Do you see how we got from that equation to this equation? This is z, this is z bar, okay, and this is divided by 2i. Yes? Now, once again that x minus x and p minus p, these are Hermitian operators. So I can move this guy to this and then this guy to this. Yes? Okay. And then I can just expand everything. So here I have x multiplied by p, and here I have p multiplied by x. So I'll have psi inner product x p minus, so p x minus x p minus, oh no, plus p x. Okay? And all of this applied to the side. And now here, on the other side, I'm going to have minus the exact same thing, modulo a small difference. Modulo the difference is going to be that this is, instead of xp, is going to be px. Because p and x and p don't commute together, so this is going to be px. But this is the expectation value of p and expectation value of x. This is just a number multiplied by a number commutes with linear operators. So this is going to be psi. So I close this bracket, I open a new one, I'll have psi minus, so I'll have px. And once again, I'll have, maybe I'll have them in a different order, but that doesn't matter. Plus, and this is also. Do you agree with this? I just kind of move this bracket onto this side, this operator onto this side, and then expand it. Do you agree? Okay. Now let's trace very carefully which things cancel. Right, so why did I need to move everything to the other side? So I have psi in the first entry here and psi in the first entry here, so that I can now use linearity and subtract kind of this from this. Right, because it's linear in each entry separately. Okay, so I have to make sure the entries are the same so I can do the subtraction. Yes? Very good. Oh, this cannot be fully seen on camera at the end of this. Okay, that's fine. So now what cancels out? P, this is a number times x. This is the same number times x. Same sign. So this cancels out. Okay? This cancels out with this because it's the same term. And this cancels out with this, which is the same term. Yes. So I'm just left with psi inner product x composed with p minus p composed with x times psi inner product divided by 2i and absolute value of the squared. Do you agree? Yes. That's true. Now we have to finally come back and use the third fact that we haven't used. The third fact is what? That this is I bar. Okay, and psi inner product psi is what? 1. Okay. So this minus this is I bar. So I can factor it out. I can get I bar divided by 2i all squared. Do you agree? This gives me h bar, h bar squared over 4. Okay, and where did we start off at? We started off sigma x squared times sigma p squared is greater than or equal to h squared over 4. And if I was to take the square root of both sides of the equation, I'll be left with sigma x, sigma p has to be greater than or equal to h bar over 2. Okay. And so this is the big result that we did. Okay, the calculation seems long, but once again, it really has only 3 steps. You apply Cauchy-Schwarz, then you only leave the imaginary part of your complex number in the norm, and then you use this fact. Like there's 3 steps. It's just that, oh, I have 4 terms. Oh no. And this is the uncertainty principle. The fact that the uncertainty in your measurement, in measuring x, times the uncertainty in measuring has to somehow be greater than some constant number. And this really tells you that, okay, if I am, like, right, these uncertainties kind of tell you how close your measurement is, the measurements that you can potentially make are close to the average, right? And this is saying what? This is saying suppose sigma x is really small, right? That means sigma p has to be really large because of this inequality. Do you agree? So this means that if we do a bunch of measurements and we're rather sure that the position of the particle is here, right? Then if we start doing measurements on the momentum, then there has to be a much greater spread for the momentum that we can measure. Right? So this is very much exactly like what you always hear everywhere, that if you're sure that the particle is here, then you can't really measure its momentum anymore. Like you can't really be sure, sorry, I'm being unclear, that if you know for sure that the particle is somewhere, so this uncertainty is 0, that means sigma p has to be kind of arbitrarily large, infinite. So we demand this inequality. Okay? And we will see this in more detail next week. So this is we derived the uncertainties. Okay. See you next week.